So I don't know if we have any English people out there. I found this haiku and I thought it was really funny, so I wanted to share it with you. And the good news is that today we're going to be talking about more meanings for this letter P that we're going to keep using. So I thought it was maybe an appropriate time to throw this at you. And today we're going to be talking about chapter 21 and kind of thinking about where we've been, where we're going, and how this relates. So the first few slides here are maybe not following your notes directly, but I'll let you know when we're jumping in there. But just so you know, chapter 18, of course, you remember back to that, we talked about inference for a population mean. So again, by inference, I mean confidence intervals and hypothesis tests. And then last time we talked about, in chapter 20, we did the same idea with a population proportion. So based on the thing that we're interested in looking at, we had methods for both of those. So back in chapter 19, we did, what if I, instead of just looking at one group, what if I want to compare two groups, and specifically comparing two means. Chapter 21, guess what? We're now going to be comparing two proportions. So borrowing ideas from actually both chapter 19 and 20, we can kind of do the usual things here for chapter 21. And so it's kind of a example to get us thinking about this, why we might need to use these techniques. Think about this. According to a Gallup poll conducted back in 2001, 63% of Americans were either fairly concerned or greatly concerned about global warming. And then we asked the same question in 2011, and we found that the corresponding proportion was 51%. So we went from 62 down to 51% of people are somewhat concerned, at least, about global warming. And this indicates that maybe Americans are worrying less about environmental issues than before. So back in 2001, more people were concerned about this than in 2011. So thinking about if we wanted to kind of answer this last question here, so turn that into a question. Are Americans worried? Are we worrying less about environmental issues than we were before? We want to do the same kind of thing. So if we want to estimate if there is a difference in the proportion of Americans concerned about global warming, how can we estimate this difference? So if we want to, let's let P 2001 be the proportion in 2001 concerned with global warming, and P 2011 be the proportion in 2011 concerned So just setting up some notation. How would we estimate, let's say, the difference here? So going from 2001 down to 2011. How would we estimate that difference in proportions? Just kind of intuitively, maybe without looking too much further ahead in your notes. How would we give just a single number to estimate that difference? Yeah. Yeah, exactly. So take the 63 minus the 51%. So that maybe in symbols that would be our estimated proportions from each of those groups. So we take p hat 2001 minus p hat 2011, which is the 0.63 minus 0.52, was it? 51. So kind of that usual idea that if we want to estimate the population something, we can use our corresponding estimates from our sample. So if I want to estimate the difference in population proportions, I can use that. I can estimate that using the difference in sample proportions from each of my groups. So just kind of using the same ideas that we've been using all along here. So I'm going to throw this table up here again. This is not, again, formal in your notes, but it's things that we looked at from last chapter. Just kind of reminding you that when what we did when we had a difference in means and when we had proportions. So here's this is chapter 19, this is chapter 20. So again, down here in chapter 21, you can kind of see where we're going here. We want to find a formula for how to construct a confidence interval. Again, remember, we don't want to give just a single number to estimate this difference in proportions. We want to give a range of values. And then similarly, we might want to, just like we did back in chapter 19, we might want to do some sort of a test. Is there a significant difference between our two groups and the sample proportion now? So this is kind of where we're going. And of course, I'll throw this slide up here again. I've seen this a number of times now. So we're going to be doing the same thing that we've done before, right? For our confidence interval, we're going to take our estimate plus or minus some critical value times a standard error. Just need to figure out what each of those things are. And for our test of significance, we also need to figure out what is our test statistic and how do I find a p-value. And after I've found a p-value, my interpretation is essentially the same as it was before, just kind of using the language of whatever the specific example is. So again, this is that's the nice thing about this class is we're kind of building on what we've already done, just kind of introducing methods for new types of problems. So again, if we want to construct this confidence interval and then also the test statistic, we need to understand the sampling distribution of this difference in proportions. So same idea, if we wanted to, when we were looking at a sample mean, we had to figure out what the sampling distribution was there to be able to construct our confidence interval. So kind of thinking about how does p hat 1 minus p hat 2 behave? Kind of what will that look like? Okay, so I think we're bringing us down to the bottom of the first page, ready to move on to the second page of your notes. Kind of jumping into the formula. So thinking about, again, if we want to do this confidence interval, we have to kind of understand how our estimate's going to behave, and that's where the sampling distribution comes in. So again, going to give you some facts. We're going to kind of gloss over some details. Again, we'll leave this for your later stats course that you take. So the first thing to know is that when our samples are sufficiently large, we have that caveat again. The difference of proportions, this p hat 1 minus p hat 2, is approximately normal. So again, remember p, the hat on top, we're calling that p hat. That's at least our second meaning of p, right? If not the third. So just to remind you of our notation. So we have this thing that's approximately normal going on. That's good. We know how to deal with that. The mean of our sampling distribution is exactly what you would hope it is. It's P1 minus P2. So that's what we're trying to estimate. So again, the mean of the sampling distribution is going to be the correct thing. And our standard deviation is this kind of weird looking thing down here at the bottom. Although you can maybe think about how that relates to what we saw in chapter 21. We have P1 minus times P1 times 1 minus P1 over N1. And then the same thing from the second sample. So this is again from population 1, and this is from population 2. So same as back in chapter 20, does anybody see a problem with the standard deviation that we have here? Or if we want to actually use this thing? Yeah, Sarah.
It has the p, which is what we're trying to find in it.
Exactly right. So this depends on both P1 and P2, which we don't know those things. So just like before, I've gotten ahead of myself. Let me skip ahead here. Never mind. I won't skip ahead here. Hold that thought. This is a picture quickly of what the sampling distribution looks like. So again, down along the axis, the horizontal axis there, we're going to have values of our estimate, p hat 1 minus p hat 2. And again, it looks kind of has that nice normal shape that we've seen before. The mean, the center of that thing is what we're trying to estimate, P1 minus P2, and then kind of says what the standard deviation there is. So just to remind you that this, when certain conditions check out, this is kind of the picture that the sampling distribution would look like. And we want to use this to construct our confidence interval, same way that we did before. So here in this chapter, again, we're going to have two confidence intervals to consider. A large sample confidence interval and a +4 confidence interval. So again, we're going to have the same two things that we saw back in chapter 20. And let's see what these things are. So kind of the general setup here is that, again, if we have our favorite simple random sample of size n1 from our first population and a independent simple random sample from the second population, when we have those samples that are big enough, we're going to have an approximate level C confidence interval for the difference. And what's that going to be? So again, same idea as before. We have our estimate plus or minus the critical value times the standard error. Probably getting really tired of hearing me say that formula. But again, so here our estimate, as we said, is p hat 1 minus p hat 2 plus or minus a z star. Remember, we have a normal distribution here. So we're going to, again, use the z here instead of the t like we did back in chapter 18, 19. And then times the standard error. So kind of the same intuition that we've been using all along. Again, because our sampling distribution is normal, we can use a z star here. So it's going to kind of be the same, again, kind of going back to that slightly easier way, I think, of finding critical values. Again, we're using a z star here because our sampling distribution is actually normal, or approximately normal anyway. Okay, so what is the standard error here for this thing? Again, just like we said before, the standard deviation that we saw previously, we can't actually use that because it has P1 and P2 in it. So again, we have to estimate that standard deviation, which what we call the standard error, and it's going to look almost exactly the same as the standard deviation. We're just throwing in our sample proportions there. So instead of P1 and P2, we have P hat 1 and P hat 2. So not lots new here. This should be what you expected. And then again, we want to use this interval only when the number of successes and number of failures are 10 or more in both samples. So I think for this confidence interval in chapter 20, we wanted it to be at least 15. When we have two samples, they only have to be 10 or more. So the conditions start to get slightly even more complicated. So again, we still have the same two conditions. Random sample, small enough sample are going to be the same as they were before. Just want to make sure we have random samples for each of these groups. And just like chapter 19, are the populations of interest. So are both populations at least 20 times larger than our sample size. So we want to make sure both of our samples are small enough. And then the large enough sample, we want to make sure we have at least 10 successes and 10 failures in each group. Which means that we want to take n times p hat 1, n1 times p hat 1. We want that to be 10. n1 times 1 minus p hat 1 to be at least 10. Same for the second group. So that's our large enough condition for this difference in proportions. Again, the first row is our n times p hat 1 is the number of successes we have in that first group. N1 times 1 minus p hat 1 is the number of failures in that first group. Same for the second group. Any question you guys can think of so far on either the formula we're using here or what the conditions are asking for? Oh, okay. Question came in a few minutes ago. Sorry. So let's go back. It says, what exactly is the difference between p and p hat in this case? So again, remember that this is kind of like let's remember what we did in chapter 18, what we did in chapter 20. We have our parameter and our estimate. So in chapter 18, we were trying to estimate the mean, which we called mu. And we estimated that using the sample mean, x bar. So again, population, we wanted to estimate the population mean with the sample mean. And so we have the same idea here. We're using the same letter, I guess that is definitely more confusing. But down here with proportions, we're estimating p, which is the population proportion. So the population proportion, and we're estimating that with p hat, which is the sample proportion. So before we were always using Greek letters for our population things. We had mu and sigma, estimate those with x bar and s. We sort of dropped that Greek letter notation, and p without a hat on it, remember that's our population proportion, so that's something we don't actually know. It's what we're trying to estimate. And p hat is our sample proportion. So of our sample that we take, what proportion of that sample is the proportion of what the population that we're talking about there. So then in this chapter, again, P1 and P2 are just, we're putting a subscript on there to talk about which group we're talking about, and then P hat 1 is our sample proportion from that first group, P hat 2 from the second group. So if that didn't clarify things, please let me know. Any other questions, comments you guys can think of? Or did I skip through a slide too quickly there? Okay. All right. Well, let's use an example. Let's do an example here, and kind of continuing that thing we started with this morning, and show you kind of what we're talking about here. So, using that same example that we were saying before about are Americans concerned about global warming, more or less so than they were in 2001? Let's now calculate a 95% confidence interval for that difference in proportions. So let me set up my notation here. So like I did before, P 2001 equals the population proportion of those concerned with global warming in 2001 in 2011 is the sort of the same thing in 2011. Then we'll have our p hat 2001 and p hat 2011 are the sample proportions. For each of those groups. So again, just reminding you that sort of what we're trying to estimate is this population thing that we don't know what it is. We're going to use that using the p-hat and the two p-hats, the two sample proportions that we calculate from each of our groups. So just kind of keeping in mind what the difference between these things are. Okay, so again, when we're looking at proportions, I think a good first step is always to kind of write down what are we calling a success. So here we're calling a success. Again, we're looking at the people who are at least somewhat concerned, fairly concerned to greatly concerned. So we'll say is being concerned about global warming. So kind of keeping that straight, what is our next step? Check conditions. Yes, thank you, Donna. So again, we want to kind of line up our conditions here and see how we're doing. So as usual, we have our simple random samples are small enough. And thirdly, are they large enough? Okay, so first of all, I guess you might need to look back to, on the first page of your notes, I totally skipped over it, but there was a short paragraph there on survey methods, kind of talking about how they got the information and listing the number of people we have in each group. So do I have simple random samples? If you flip back to there. Any thoughts? Do I have simple random samples here? Any thoughts? Do I have random samples here? Does it say so? It does not say so, right? So that's our usual bailout is no good here. So it doesn't say. So then what do we do? So again we don't. It doesn't have to be a random sample. That's kind of the best check. What we really need is a representative sample, right? And a random sample is kind of our way of getting a representative sample. So it doesn't say if we have a random sample, but so if it doesn't say you have a random, you have to think about, could this possibly be a representative sample of who I'm talking about? So again, there's a bunch of information there, and of course, and we also have that these polls they're a Gallup poll, right? And Gallup is, at least hopefully, this good polling organization who does good things. So you would hope anyway that they have chosen representative samples. So even though we're not told that these are independent random samples, it's safe to assume that they are representative of the population. So safe to assume that the samples are representative because this is a Gallup. It's a Gallup poll. So again, we're trusting our polling organizations, which maybe that's a good idea, maybe it's not, but we would assume that they've done some good work to make sure they have a representative sample when they publish these results. So even though it doesn't tell us there's a random sample, again, we kind of think about, well, that's probably okay to assume in this case. I'm going to run out of space here, so let me move this down. So we're good to go with our representative samples anyway, even if it's not a random sample. Small enough, we need to take 20 times our first sample size and 20 times the second sample size. So let me let me stick with the subscripts I had before, N 2001 and N 2011 being the sample sizes of each of those years, from each of those years. And if you look back, the sample size from 2001 was 850, I think. Yeah. So in 2001 we took 850 people, and in 2011 we took 1,021, which is 20,420, and and 17,000. So how do those numbers compare to our population sizes in each of those years? So again, who is our population in both of these cases? Yeah, exactly. We're trying to say something about all Americans, right? So are there more than 17,000 and 20,000 Americans? Well, of course there are. This is less than all Americans in each year. So we're good to go with the small enough condition. And then quickly we need to make sure that we have enough successes and failures in each group. Let me jump over to a new slide. So our large enough, again, we need N1, N 2001 times P hat 2001. And our number of successes, our number of failures from 2001 as well as from the second year. So 2011. So we want to make sure each of these things is bigger than 10. And so here we had 850 times 0.63, 850 times 0.37, 1021 times 0.51, and 1021 times 0.49. And I'm going to skip writing out exactly what those are. I'll let you punch those into your calculator, but you can easily see that each one of those is bigger than 10. So we're good to go with a large enough condition as well. So I just had a question come in on the back channel. Is the population all Americans or all adult Americans? And I think I probably misspoke. So this should probably be all adult Americans from each year. You guys are really good at keeping me honest here. In the survey methods, it does say we're basing this on telephone interviews with adults. So that's a very good catch. Thank you. Questions, comments about the conditions we checked, or anything that we've set up here otherwise? Okay. Enough checking conditions. Uh-oh. You guys all written down the large enough condition? Can I erase this? I didn't have another extra slide there. Writing too big. Can you really?
Oh, not I mean, like with the eraser.
Oh, with the eraser? Maybe I have a crappy tablet. I don't know. Anyway, all right. So again, we've checked our conditions. We're ready to go. We can use our formulas now. So the confidence interval is going to be p hat 1 minus p hat 2 plus or minus z star times our standard error, which I will go ahead and write out. That's, again, the square root of p hat 1 times 1 minus p hat 1. I don't want to write out 2011 and 2001. So this is going to be from 2001, and this is going to be from 2011 over N1 so I'm throwing in 1 and 2 instead of 2001 and 2011. So again, my estimates are 0.63 minus 0.51 plus or minus. What's my z star if I want a 95% confidence interval? Very close. 1.96. Check the table, right? That's our so Alyssa was very close. 1.96, and then we can do this big calculation. We have 0.63 times 1 minus 0.63 over 850 plus 0.51 times 1 minus 0.51 over 1021. All that under the square root. And this is going to be 0.12 plus or minus 0.045, which is 0.075 to 0.165. So there's my 95% confidence interval for the difference in these two groups. So we're not quite done yet, right? So now we want to make sure to say exactly what those two numbers mean. It's great that we made the calculation, but let's say what they mean. If I'm right at the bottom of the slide, can you guys see that? Should I go to the next slide and do the top? Is the bottom okay? Bottom all right? All right. So what we can say is here we are 95% confident. That, and now we want to kind of say what these two numbers mean. So remember, we're talking about the difference from 2001 to 2011. So the proportion in 2001 is going to be larger. Between those two numbers, that much larger than it is in 2011, right? So the proportion of concerned is between 7.5% and 16.5% higher. And now that's getting too small, so I'm going to come up here. Higher in 2001 than it was in 2011. So again, I have 95% confidence that the proportion of concerned adults concerned about global warming is between 7.5% and 16.5% higher in 2001 than in 2011. So that should feel like a fairly comfortable interpretation. Again, it's almost exactly the same as we've done before, just kind of plugging in the specific example that we have here. Are there any questions you guys can think of on calculations or the interpretation or anything like that? Okay. So that was our first method, just kind of like we had back in chapter 20. Again, if that large enough sample condition does not check out, again, we do have sort of a backup method, and this is going to again be that +4 method that we have seen before. And again, kind of the main thing to think about this, and the main time that we're going to use this is when that large enough condition for the first procedure we just looked at, when that does not check out, this is kind of our backup of what we can do. Instead of just saying proceed with caution, throwing up our hands, here's our backup strategy. So again, same setup. If we have two independent simple random samples, if we want to do a +4 confidence interval for that difference, we're going to add in our 4 imaginary observations. This time, however, we're going to do one success, so two observations in each group. One success, one failure in the first group, one success, one failure in the second group. And then the formula is going to look identical to what we saw before. And so I'll show you that on the next slide, but here's the reason that this is kind of our backup strategy, is that we can use this when just the sample size is at least 5 in each group. So regardless of how many successes and failures we have, as long as our sample sizes are at least 5 in each group, we're all set for this. And again, it'd be hard to think of a situation when you didn't have at least 5 people in your samples. That would be really, really small. So this will be useful almost always. Okay, so again, here's our formula. It's p tilde 1 minus p tilde 2. So to see what these are down here below. And again, p with a squiggle on top of it there, we're calling that p tilde. So just to denote that this is different than p hat. So again, formula looks almost exactly like it did before. Just down here when we're calculating our sample proportions here, we're adding one success on to the first sample, dividing it by the number in that first sample plus 2. So we're adding 2 observations there. And similarly for the second group, we're adding 2 observations, 1 success, and then 1 failure. So 2 total observations there to that second group. And the standard error formula looks about the same as it did too. We're just, again, remembering, like I didn't last time, to add in those put in our sample size there on the bottom. So N1 plus 2, N2 plus 2. And then just to kind of formally list here again the conditions that we need to check, we want to make sure that each of our sample sizes are at least 5. So the first 2 conditions, as usual, stay the same, and we can just make sure we have 5 in each sample there. Okay, so let's go ahead and try applying this thing. So here, the next example, we're talking about air pollution. So in a study of the effect of air pollution on lung function, a sample of 25 children living in a community with a high level of ozone pollution, we looked at their lung capacity. And we find that 7 of those 25 have a lung capacity that's below normal for their size. So that's our first group. Our second group is we're looking at 40 children from a community with a low level of ozone pollution, and we find that 6 of them have lung capacities that below normal for their size. And so again, we want to construct a 98% confidence interval. We'll throw a different confidence level at you there. And we want this confidence interval for the difference between the proportion of children living in the high ozone community and the proportion of children living in the low ozone community, thinking about their lung function. Okay, so thinking about here, again, just going to formally write this out, is that a success in this example is not really a success at all. It's having a lung function below normal. So we want to compare our percentages from each of these groups that have sort of below normal lung capabilities. Okay, so our conditions, next step is checking conditions. We have, do we have a simple random sample? Are they small enough? And are the samples also large enough? So to get you guys involved here, what do you guys think? Do I have simple random samples, or at least a representative sample? Seeing some nodding heads. Does it say that we have random samples? It does not say that we have random samples. Is there a reason to expect that it might be a representative sample? Who knows, right? So can't say. So it's not stated, and we're not sure maybe if these are representative. So here we do kind of have to, unfortunately, do the usual bailout of, well, we can proceed with caution as far as that first condition. So again, we don't know. It's not stated if it's a random sample. We don't know that it's even necessarily representative, but again, sort of for lack of anything better to do, we can at least kind of see what the results are and then go from there. Yeah, and air pollution is a serious problem with lung function. Yeah. So we're not sure if we have representative samples, but are our samples small enough? So we have we want to take 20 times n1 and 20 times n2. So from the first group, let's say group 1 is the high ozone, and group 2 is the low ozone. So in the first group we had 25 people in our sample. In the second group we had 40. So 500 and 800. So how do those numbers compare to all the children living in those communities? Again, who knows, right? But we're gonna hope that our community is somewhat of a good-sized city, right? So we can say here that this is probably, we'll put a probably here, probably than all children in these communities. So usually we just run through these conditions, say check, check, check. Here we're not sure. So we might, again, maybe would say proceed with caution, but we're, again, probably in good shape here. And then for the large enough condition, I'll leave it to you to check that the conditions for the other confidence interval fail. And again, N1 is 25 rather, which is bigger than 5. N2 is 40, which is bigger than 5. So we're good to go sort of regardless. Got to get blinded by the sun up in here. Okay, so again, our small enough condition and large enough condition are both fine. Random sample, maybe not, but let's kind of see what we can do with this. So if we want a 90, well, let's first calculate our p tilde 1 and our p tilde 2. Again, the first group we had 7 children with below normal plus 1 divided by 25 plus 2. So 8 over 25 is our new proportion here, which is 0.296. In the second group we had 6 successes plus 1 over 40 plus 2. That's 7 out of 42, which is 0.167. Now we're ready to plug these things into our formula, right? So we have p tilde 1 minus p tilde 2 plus or minus z star times this big square root mess, p tilde 1 times 1 minus p tilde 1 over n1 plus 2 all that under the square root sign. And again, so we're asking for a 98% confidence interval here. So we don't have one of our usual 3 things there. So I'll just tell you what it is. If we want 98% confidence, z star is going to be 2.326. So I will leave that as a homework problem for you to go make sure that you can figure out what that is. Let's quickly plug this in. So we have 0.296 minus 0.167 plus or minus 2.326 times 0.296 times 1 minus 0.296. Struggling to write today, aren't I? Over 25 plus 2 plus 0.167 times 1 minus 0.167 over 40 plus 2, square root of all of that. If you punch that into your calculator, you will get 0.129 plus or minus 0.244, which is negative 0.115 up to 0.373. So we've come through all these calculations, and there's our confidence interval. It has negative numbers in it. Is that a problem? Have we done something wrong here? Of course not, right? Because it's written up here on the slide. Right? So that is actually okay. So our confidence intervals in this chapter, if they're negative, that's not a problem. Think about what that means. So I'm not skipping over this. I just want to find some space to write this down. So ignore this for now. So again, our confidence interval for P1 minus P2 is negative 0.115 to 0.373. So let's write down an interpretation for this quickly and convince ourselves that that's an okay thing to say. So what we'll say is that we are 98% confident that the proportion of children with low lung function is between 11.5% less and 37.3% more than the proportion in the sorry, I've made a typo here, righto. So I meant to say high first. Oh no, I'm butchering this whole thing, aren't I? And I'm out of time. I'm sorry. I'll come back and touch this again on Friday, guys, and I will make sure that I have a good interpretation here. I'm really sorry. It's a very unsatisfying way to end class, but have a good rest of the day. We'll see you guys on Friday. Or I will write this out now if you want to stick around for it. Low long function. Function. Low. Too many highs. Too many highs and lows in there. Oh boy. That is a confusing one.